Hi guys, and welcome to the Daily Maths Challenge, episode 7. Today we're going to go through units and converting between them, so let's get started. Now the bronze question says convert 1,000 kilometers to meters. So what we need to do to get started is just remind ourselves, we just need to remind ourselves how many kilometers make up a meter, or vice versa. So we know that 1,000 meters is equal to 1 kilometer. Kilo, the prefix kilo is basically a way to say 1,000. So we have kilogram, which is 1,000 grams. And kilometer is 1,000 meters. That's just a simple way for you to memorize this fact. And so, but we need to work out, okay, well, if I have 1,000 kilometers, how much is that in terms of meters? Well, to understand what to do, 1,000 kilometers is like 1,000 lots of kilometers. Imagine 1,000 kilometers stacked side by side. Well, in each of those kilometers, you have 1,000 meters. So really, what we have is we have 1,000 lots of 1 kilometer, which is 1,000 lots of 1,000 meters. Now, 1,000 lots of 1,000 is a million, or 10 to the 6. So let's just say I'm going to have 3 zeros here. That's a million meters. Okay, so it's a lot of meters. All right, on to the next. Convert kilometers squared to meters squared. What we're looking at here is area, okay? Basically, a kilometer squared, just like a centimeter squared, I think we've seen that on a previous episode. If you're looking at a kilometer squared, that's like the area that makes up a square whose sides are 1 kilometer in length. Now, obviously, if we get that same length and divide it into meter squares, we're basically going to count how many, if we zoom in, how many of these little meter squares fit into this original 1 kilometer square. So there are going to be a lot of them fitting in. And so how will I explain this to you? Okay, so let's just briefly talk about what happens when we go from one unit of measurement when it comes to length to another one. So if I have, let's just focus on meters. Actually, wait, no. Actually, I'm going to do centimeters and millimeters, okay? So let's look at 1 centimeter squared. Let's say that I draw them here and here. Well, we know that in a single centimeter, I'm exaggerating obviously how big this is on my page, but let's pretend this is a centimeter long. Then we can divide this up into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, we can divide it into 10 millimeters. So each of these guys is going to be a millimeter long. Now, you don't be tempted to think, okay, well, because I know that 10 millimeters is equal to a centimeter, don't be tempted to think that 10 millimeters squared is going to be a centimeter squared, like you times by the same number. That's not true, and actually we can look at it here. So if you think about 1 centimeter squared, sorry, I realized I made a mistake. If I said cubed here, forget that. 10 millimeters squared, centimeter squared, that's how you say that. Anyway, so in a centimeter square here, let's think about how many millimeter squares fit in, okay? How many millimeters squared fit into a centimeter squared? So how many do fit in? Well, this length here is 1 centimeter long, and as I said, this 1 centimeter is going to have 10 millimeters in it. So I'm just going to divide this into 10 strips, okay? So I've divided this into 10 strips, but this was a centimeter, so really this is actually going to be 10 millimeters long, okay? And likewise, I could do the same for the top. So I'm just dividing that into 10 parts as well. Okay, let me just check if this is recording. Good. Many times I've started rambling and talking and realized that I'm actually not recording, which isn't It's always a highlight of my day. Uh, okay, so I've divided this same square into, well, I've got the same shape, except I've divided it into strips of 10 and strips of 10. So clearly, if you think about how big each of these little squares is, if we zoom in, well, we know that this length here is 1 millimeter long, and this length here is 1 millimeter long. So now we're ready to answer the question, how many millimeters squared, how many of these guys fit into 1 centimeter squared? This is a centimeter squared, as I said earlier. Okay, so if you think about it, you have 10 strips here, horizontal rows, and we have 10 columns. So in each row, you have 10 millimeter squares. You have 10 of these in each row. And because you have 10 of them, 10 rows, you have 10 lots of 10 millimeter squared in the whole thing. So we're going to have 10 lots of 10 millimeter squared in a centimeter squared, and that's going to be equal to 100 millimeter squared equals centimeter squared. Now look at this. Even though 10 millimeters fit into a centimeter, that's units of length. Actually, 100 millimeters squared fit into centimeter squared. It's not the same. It's actually 10 squared millimeters squared fit into centimeter squared. Okay. So when going from length to area, if this many lots of one unit of distance go into one of them, it's going to be the square of that number that is telling you how much of the kind of sort of that units of area based on these units fit into each other. Okay, so let's look at how we apply this to our kilometer situation. We know that, well, this is a kilometer squared, 1 kilometer by 1 kilometer, and this is a meter squared. Now we know that 1,000, imagine if we divided this again into 1,000 strips. 1,000 meters make up 1 kilometer, and I did it also with this portion here. Well, I'm going to have, how many little squares am I going to have? I'm going to have 10,000 times 10,000, sorry, 1,000 times 1,000 meters squared fitting into a kilometer squared. That's going to be 1,000 squared meters squared, and which is also, if I want to write out all of that, all of those zeros, it's going to be 1,000,000 meters squared fitting into a single kilometer squared. So although in 1,000 kilometers we have 1,000,000 meters, in just 1 kilometer squared we have 1,000,000 meters squared. Okay, and actually, because we can kind of compare this earlier, if I wrote down 1,000 meters is equal to a kilometer, can you see that to go from looking at meters and kilometers to meter squared and kilometer squared, we've actually squared this number here to find out how many are inside the other. Okay, that's a really important fact, and this works in general for looking at going from units of distance, converting between them to converting between units of area. Okay, that's the bronze one. Let's now go to the silver question. So oh gosh, that was the silver question. I need some more sleep. The gold question. Okay, so 2 hollow cubes, each with a very thin surface, are being used as water storage tanks in my garden. I need to paint them both, but I have a tight schedule and I need to know if I have time to paint the big cube. In the past, I filled up both, blah blah blah. Basically, the big one takes 100 times as long to fill up with water, and I know that it took me 5 minutes to paint the smaller one. And how many? If I have 2 hours before I have to leave the house, do I have enough time to paint the big cube? So there's a lot going on here. So let me just draw. Let's move my camera down slightly. Okay. So I have 2 cubes. So let's say a really small one, and then a really big one. Okay. Now they're both cubes. Now the really important fact with these cubes is that if you think about these cubes as being the same, it's just that we're enlarging them. You can get from one cube to the other because they're the same sort of shape. You can't enlarge, like let's say a sphere into a cube with a normal enlargement, because one sort of type of shape will map to another shape in enlargement. We're going to stretch it, but a cube doesn't become a circle, a sphere, and vice versa. It's important that we're mapping to the same type of shape. And because we've got two cubes, we can think of a transformation from one to the other. Now that's important because with the theory of transformations and enlargements comes the knowledge of how do we scale, for example, surface area, which is the area on the outside. That's the what we're going to be painting, right? The surface area of this object. So enlargement will help us think, okay, how much is the surface area going to be enlarged by? How much do we times the surface area by to get the surface area of this one? That's going to help us answer how much longer it's going to take to paint this one, because painting a surface, in order to work out how long it takes, you need to work out how long it takes for you to paint a square of a centimeter, let's say, dimension each, and how many of these centimeters squared are on the outside, i.e. the surface area. So let's look at this. I know if we're looking at volume now, I know that this one is 100 times longer. It takes 100 times longer to fill up this one compared to this one. Okay, say volume times 100, right? I just need to times that time by 100, because the volume of this one is going to be 100 times bigger than that one. Because assuming that I'm filling up with water at the same rate, this one has to have, if there are, for example, 10 centimeters cubed. Remember, centimeters cubed is the unit for volume, if we're using centimeters. Centimeters cubed, there must be 100 times more of these centimeter cubes in this one, okay? So we know that the volume is 100 times bigger in this one compared to this one. Now that's really important. Now, if you think about it, so I'm not going to explain a lot of this, I'm just going to go for the answer. Let's say that I get this cube from this one by timesing the lengths by, let's say, A. Okay, so if this length is 10, this is going to be 10A. And if this length is, it has to be 10 or 5 or whatever it is. If this is 5, it's going to be 5A, for example. If this length here, the diagonal, is 16 or whatever, this is going to be 16A. Okay, so I'm timesing the length of this by A to get this one. Now the fact is, as we saw earlier, if we're timesing a length by a certain number, then we know that the area is going to multiply by, units of area are going to multiply by A squared, okay? And volume is going to times by a to the power of 3. That's just a fact, and I'm not going to explain it. I encourage you to learn a bit by yourself if you don't know why that's true. So the volume is going to increase by a to the power of 3 if you think about the transformation from here to here. Now this is really important. So because we know that we're timesing by 100 to get the volume of this one from this one, we know that that has to be equivalent to timesing by a to the power of 3. So to find out what a is, okay, I'm going to get my calculator. I'm going to type in 100 to the power of 1/3, 1 divided by 3, because that's going to give us the cube root of 100. So that gives me that answer. So that's what a is, okay? A is 4.64 blah blah blah, okay? Now what I'm going to do next is, okay, well I know that area is I'm going to times by a squared, okay? And that's really important because basically if the surface area of this is 10 centimeters squared, for example, then the area of this is going to be 10a squared, i.e. it's going to take a squared longer for me to paint this one compared to that one. So if this takes me 5 minutes, this is going to take me 5 minutes times a squared. So that's a. I'm going to square that answer, giving me this, and this is how much longer it is going to take me to paint my big cube compared to this cube, right? Because the surface area is measured in centimeters squared or whatever its area fundamentally. Okay, so that's how much longer it's going to take for me to paint the big cube, and it took us 5 minutes to paint the old one. So we're going to times by whatever that is, 21.5 or blah blah blah. I'm going to times that by 5 minutes. And how many hours is that? Well, that's how many minutes, so I'm going to divide that by 60 because I want to work out how many 60 minutes goes into that, i.e. how many hours go into that. And that's going to give me 1.79 blah 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 hours, Okay, so I'm gonna round that to 1.8 hours. So sorry, I realize you can't see that. So what this means is that it is going to take us 1.8 hours to paint the big cube, and that is less than 2 hours. So actually, we know that we will have time. Okay, in the 2 hours that we have before we need to go out the house, we're gonna have enough time to paint the big cube. Okay, so this is just an area where maths can help you. Like, I know it's a bit of a a synthetic example, a bit of a contrived example, but in reality, this can really help you. But okay, thank you for listening to the Daily Maths Challenge, episode 7, and I look forward to seeing you tomorrow, hopefully. All right, thank you. Bye.